Okay, well, we have a second award winner. Next slide, please. Larry Nyquist. And I have some things to read for Larry. And Larry is here, so you'll see Larry. Larry spent over 45 years at NASA JSC as a planetary scientist, specializing in measuring the ages of Apollo lunar samples and Martian and other meteorites. His groundbreaking approach and methods resulted in detailed chronology of key events in lunar and Martian history. But more importantly, he established a mindset or philosophy seemingly obvious in hindsight, but little recognized before his work, that the true value of a rock's precise age date comes from linking it to a geologic event. This profound influence has affected the course of planetary science, not just from within NASA, but across the global scientific community. Dr. Nyquist's contributions represent sustained performance that have resulted in major improvements, both to NASA deliverables and image. He has set the benchmarks for understanding the timing of geologic events in the solar system, especially for the moon and Mars. This work, documented in hundreds of heavily cited papers and conference abstracts, continues to influence the success of NASA's efforts in the field of planetary science. Two specific examples support these statements. First, in the early 1970s, most planetary geochronologists settled for obtaining reliable ages of the samples they studied, with less attention paid to the geologic history of the sample's parent body. Larry recognized that a significant geologic event even the best determined ages is of little value unless it can be linked to a specific geologic event. His work showed that many element pairs used for age dating are subject to resetting during energetic impacts, possibly clouding the geologic picture. His approach became the standard during the 1970s and early 1980s. Secondly, Larry helped establish that the basaltic Martian meteorites are in fact only a few 100 million years old, and most other meteorite types are well over 4 billion years old. This finding led to an eventual understanding of how Mars formed and differentiated. He showed a strong linkage between these rocky formation ages and the exposure ages, implying that the Martian meteorites likely reflected only a few magmatic sources on Mars. That is, subsets of them were likely launched by the same impact event. Here again, this paradigm has come to govern our thinking about those processes, and such assessments have become the norm for all research performed for similar studies. Dr. Nyquist's contributions have led to a deeper understanding of the geologic histories of the moon and Mars. His thorough, methodical approach is a model and benchmark for 2 generations of succeeding planetary scientists, both inside and across the world. His approach directly influences planning at the earliest stage for study of return samples by future robotic missions. Just which samples must be examined in the first place? Accordingly, the Shoemaker Award, reflecting the scope of SSERVI, is a richly deserved award for Larry's many accomplishments. Please join me in congratulating Larry for this award. Okay, and Greg, please.
Yeah, so I was gonna. Yeah. Okay. A second pudding.
Second
pudding. Oh, okay,
okay. Yeah, yeah. I want to make sure I don't get you.
Do I do it this way?
Very good.
Okay, so, well, thank you, Carly, and thank you to anyone who might have been involved in getting me this unexpected award. This was really a surprise when I got the email from Greg, and I thought, this can't be right. But I appreciate it so much, and I hope I can in some ways live up to the expectation that this introduction introduced. I didn't know I did. Uh, okay, if I can get this to work correctly, okay, or it's probably best if I just ask to advance the slide. Will someone advance the slide for me? The next one, please. Or let's see, I can do that. Can I do that? The green arrow. Okay. So I want to begin by paying tribute to the man for whom this award is named, Dr. Eugene Shoemaker. And being at JSC, I have access to a lot of the photography of the Apollo days. So I was able to get this nice photo of Gene with Apollo astronauts Dave Scott and Buzz Aldrin at the Nevada test site back in 1965. I'm sure there are people in the audience who weren't around at that time, but in this photo, Gene is teaching the astronauts about non-volcanic rocks that come from non-volcanic craters in preparation for the study of lunar impact craters. So let's see if can I advance this? That works. Okay. And at that time, or about at least within a year that time, I was in Germany at the Institute of Crystallography at the Swiss Eidgenössische Technische Hochschule, and my advisor in physics was Peter Signer, but he arranged for us to, let's see, oh, I got to find out where the pointer is. Oh, okay. I guess I'll miss some of the pointers. So we had the opportunity to go on a field trip. For physicists, this was a unique thing, a field trip to a crater, which was in Erdinger, Greece in Germany. And at that time, we learned about the sphalerite, which is an impact melt rock. And as it was soon discovered that the rocks from, at least from the Apollo 14 site, were impact generated rocks. In recognition of Dr. Shoemaker's contribution to the NASA program, he received a certificate of appreciation, shown here, being presented by Dr. Gilruth, who was the director of NASA's Manned Spacecraft Center, now known as the Johnson Space Center. This already in 1969. And of more direct importance to me and my going to JSC were Paul Gast and Jerry Wasserberg, and who are shown here admiring a football-sized rock. I think this is in Paul's office in Building 31 at JSC. People in the background, left to right, Mike Duke and Tony Callio. As you can see, Jerry's looking at this rock, which I think is probably 14310. And that's important because at that, shortly thereafter, Papnastasiou and Wasserberg reported the age of this rock as 3.9 billion years, a number which became ingrained in lunar science. We got into the game by looking at a so-called coarse fine sample from Apollo 15. And this particular sample was what we call creep rich, and meaning that it was enriched in potassium and consequently rubidium, so that we could do a nice age by using the rubidium strontium technique. We found the age of this rock to be 3.9 billion years also, which by coincidence was similar to the age that Dmitri had obtained on 14310. And so that started linking. Apollo 14 was immediately linked with the Imbrium impact. And to follow on then, the Apollo 15 samples were linked with the Apennine front of the Imbrium impact. This slide shows, and I wish I had my, oh, okay. So I keep trying to find the pointer, and I'm always just advancing. Anyhow, the point of this slide is it shows a geological map from Stifler and Reiter, 2001, their review paper, and that they had also come to the conclusion that Apollo 15 creep samples were from the Apennine Bench Formation, which is found close to the rim of the Imbrium Basin. So this, in my mind, linked creep and Imbrium Basin and 3.9. So at the same time, the Caltech group had developed the lunar cataclysm hypothesis, and they used a total isotopic approach. They relied on the uranium-lead Concordia diagram, and pointed out that all the so-called terra rocks or highland rocks that had been analyzed by uranium lead at that time lay along a chord that intersected the Concordia chord at two places in the Concordia chord and the uranium lead system. One place was a so-called upper intersection, which is 4.5 billion years, and easily interpreted as being the age of the moon itself. But the second intersection was down at about 3.8 billion years, and the Caltech group coined the term lunar cataclysm, or even a terminal lunar cataclysm, for what Jerry described as being a very dramatic event. Jerry said you needed to be, if you lived on the moon, you needed to be in a damn good bunker, he said. So anyhow, the cataclysm hypothesis lived on until about the year 2000, and it was one of the main drivers for a proposal to go to the South Pole Aitken Basin, the largest basin on the backside of the moon, and obtain a sample, bring it back, and date it in terrestrial labs. You'll recognize that this sort of thing is now being done actually by the Chinese. But we had this Moonrise proposal, unfortunately wasn't funded. So then Don and I had to do something else. And fortunately for us and other sample scientists, there was a very nice Japanese orbital mission of the moon, and they were looking for the global distribution of pure anorthosite on the moon, which they interpreted as being the crust of the moon. So, and they showed that the anorthosites do, in fact, occur ubiquitously within the lunar crust at depths of about 3 to 30 kilometers. So that meant that if you had a good size impact on the lunar crust, you were apt to eject fragments of anorthosite, and thankfully for us, some of those landed on Earth, and we were able to date some of those. And now this is work that was done primarily with our Japanese colleagues, Hiroshi Takeda and Akira Yamaguchi. And so the sample that we worked on most direct, where we did the most work was this Yamato 86032. And with our technique, the samarium neodymium technique, we showed that it was about 4.4 billion years. We claim for 4.43 plus or minus 0.03s. And interestingly enough, importantly, more than interesting, importantly, the isochron goes through the so-called chondritic uniform reservoir that was established from chondrites. So this really links these samples with an early period in solar system history. Okay. All right. At the same time that we were doing samarium neodymium, Don was doing argon, and he found an age of 4.1. So this illustrates a principle that Don and I lived with for decades. That usually almost always the argon age was reset. Some people have trouble understanding the idea of things being reset, but indeed the least robust ages get reset, and argon is one of the least robust. But that's very important because that gives us the time of impact resetting, or that ties directly into the bombardment history of the moon. So, and I had the privilege of reporting some of the results we had at the Global Lunar Conference in Beijing in May and June of 2010, 14 years ago. And we were brave enough to call this the lunar crustohistory from isotopic studies of lunar anorthosites. And this slide illustrates the argon ages, which are the easiest to interpret because they are in fact reset by the in large impacts. And this seems to indicate that the lunar average age, impact reset age of a lunar meteorite is 4.2 billion years, not 3.9 or 4.0, but the average in contrast, the average argon age of Apollo samples, anorthosites of similar composition is 4.0 billion years. So this raises an interesting question: did the backside of the moon, the far side of the moon, experience a different impact history than the front side? I think that's a question well worth continued study. So moving on to what we got in our samarium neodymium, we didn't find nearly as much dispersion in the ages as you might expect. It's a more robust chronometer, so our ages were between 4.3 and 4.5 billion years, and I think there's still some controversy as to the ages of the crustoanorthosites, and we'd go back to our work with Yamaguchi-san and point out that these anorthosites aren't all the same composition, so you don't really get to assume they should always have the same age. That's my contention. Okay, to try to attempting to come up to speed with what's going on now, I looked at this nice preprint that Jim had sent out that shows the Artemis landing sites, and I would just point out that landing sites 10 and 11 shown in the box there have about the same relationship to the South Pole Aitken Basin as the Apennine Front samples, the Apollo 15 samples, i.e. the parents of the Apollo 15 samples have to the Imbrium Basin. So I claim this is analogous, and it will be really important when guys get to analyze the samples returned from the sites 10 and 11. Okay, some final thoughts then. I've just made the most important one, which is the Artemis astronauts can be expected to bring back samples to address the bombardment history of the moon. I know that they're supposed to do much more than that, but to an isotoper, that's the most important thing. In so doing, they're clearly going to improve the overall understanding of early lunar volcanism. So the next few years are going to be really exciting ones for the lunar scientists. You guys get to relive a little bit the excitement that Don participated in. Or recalled in his little reminiscence that Carly read. And finally, through these years in the what I call the natural sciences, you know, the Germans have a better word, or have a good word, which is Naturwissenschaft. In Naturwissenschaft, you have to understand all the scientific disciplines, and that's what we needed for the moon. So my admonition to young people now is to honor your colleagues, because your colleague is apt to know something you don't know, and learn from them. Reciprocally, you should share your knowledge with your colleagues. And finally, do what you love and love what you do. And here's two guys who did. So, thank you.
So we're going to do a group picture here, and I'll say a couple closing words, but the four of us, yeah.
Okay.
Yeah.
Okay. We haven't met.
We'll talk later.
Oh, okay. Okay, thank you.
Yeah. Okay, sure, I'll answer questions.
Okay.
If there are questions,
Yeah.
and we have time.
I think we have time. If people
one or
have
two.
questions, this is your chance.
Yeah. And while you're thinking of your questions, Larry, I love what you said about thanking old timers to be able to participate, but we want to thank you. I mean, I was thinking of the old quote, "We're standing on the shoulders of giants." You know, I've heard my friend Jake Bleacher use that more than once. I was kind of in awe when you were doing this presentation, how much we're doing in my institute, and the whole community rests on what you and Don and others did. It's just wow. So anyway, Bill.
Okay, so congratulations, it's well deserved for both you and Don. I had a quick comment and a quick question, just for fun. So the quick comment is, you say you have all of these photographs from back from the Apollo era. Is there any way you could give them to someone so they could put them online? I bet a lot of these photographs I would love to see. I know a lot of people from the younger generations would probably like to see too, you interacting with the astronauts and everything else. So would that be possible?
I suggest, if there's interest in that a group from the community form and sort of write a letter to the Johnson Space Center and maybe the director of Johnson Space Center, but to the lunar sample curator is the first contact point. Judy Alton, who works in the curatorial lab, and some of you know, is a fantastic resource for these, and she helped me locate some of these photos. It probably is a fairly significant cataloging effort to get them. But as you see, they are category, they have numbers on them that give the date when the photos were taken, and so you can ask for a particular number, a particular
Oh.
year.
Okay, I thought these were personal photographs. That's my mistake.
Well, no, these are the one of Jerry and Paul and the moon rock is something that I excavated some years ago in commemoration, I think, for Paul Gast. So Paul died in 1973, so that's a long time ago. But Paul's imprint on the program is just also tremendous. I mean, Paul's the guy who brought all these other great guys together. Paul and Jerry, you know the story of the four horsemen, Paul and Jerry and Jim Arnold and Bob Walker, who went up here. They were called the four horsemen, and they advocated for NASA. And that is still absolutely necessary, that the community advocates to NASA. And the other plug I want to put in is that Bill Finney. Some of you know Bill Finney, who was at NASA, did a marvelous manuscript. It's a NASA special publication. You want, and again, you can write to Judy Alt and get the number for the NASA special publication, and that must be available broadly. Anyhow, what Bill did is he really collected the stories from astronaut training, and has a wonderful. It's a wonderful resource.
Then I'll ask one. That was actually just a comment, not a question. But I have a quick question. So Don's story about his experiences with finding out the ages of the lunar rocks, it was really fascinating. Do you have any stories from that era of finding out new results from Apollo and getting all excited about it?
Well, I came to JSC a year later, so I don't have. Well, so my stories have to do with noble gases. My training was in noble gas. The only excuse I have to got into working on the moon rocks is that I knew a little bit about mass spectrometry, and Jerry and Paul thought that maybe I could be useful in Paul's lab, and so I went from a physicist training to the Johnson Space Center, and so it was a great time. I have some stories, but not of the type that Don has. So Don was in the lunar receiving lab, and by the time I came in fall of 1971, the activity had moved over to Building 31, and the new lab was established in 31, and I think it's probably Apollo 14 on. I went to 31 for curation, but at the time I was so to all of you, if there's anybody out there, any young people who consider themselves to be sort of slaves in a lab, at the time that's sort of what I was in Paul Gast's lab, because knew noble gases, didn't know beans about rubidium strontium. I learned really quickly. Well, I'd like to think I learned quickly, but with the help of one Jerry Wasserberg, who very graciously invited me out to Caltech, and I worked with Dimitri Papastasio at the time, and so I learned their secret technique. People always have secret techniques, and so we were able to come up to speed fairly rapidly. And as I said, I credit all my colleagues. I learned a lot from Jerry. I learned a lot from the people in the gas group when I came. So it was Norm Hubbard and Bridge Manzo and Henry Wiesmann, great Swiss from the ETH, but we really did have. So the lunar program was really international from the beginning, more so I think than people really thought, because and a lot of it came from say the Swiss, the aluminum.
Mhm.
I guess my story is that I participated as a proposal reviewer on the proposal to NASA from the Barron Group to go to fly an aluminum foil on the moon and collect solar wind. So the solar wind hypothesis came from okay, you get me started on too many stories, but anyway, that's for a beer somewhere. But the so there were multiple streams of expertise that went in the Apollo program, but one of a heavy stream was basically the European scientific community that is sort of based in Switzerland and Germany, and more than a big influence, I think. And the fact that Paul and Jerry really recognized the value of maintaining those sorts of connections. I should stop.
Thank you.
Thank you very
Yeah,
much.
Yeah, we should probably move on. Thank you, Larry. For
Oh,